So I'll just give a brief introduction of Professor Russell. He has a very long list of awards and accomplishments, and we don't want to spend too much time on it. But so he studied physics as an undergraduate at Wadham College, Oxford, then went on to Stanford for his PhD, and then became a faculty member at Berkeley in EECS in the mid-80s. So he's had a career of some 40 years now, and he's really been one of the leading lights of AI. He was recently elected a Fellow of the Royal Society, which is of interest in the Turing context, because Turing himself was one of the earliest Fellows of the Royal Society working on computational sorts of questions, at the very beginnings of computer science. So just this summer, I believe Professor Russell also became a Fellow of the Royal Society. He also is an OBE, which is similar to what we call like Padma Bhushan, one of the highest civilian awards in the UK. He has fellowship of many of the eminent societies, the AAAI, and National Academies of Engineering. So he has a lot of the standard awards and recognitions, of eminent researchers in this area. He's perhaps best known for his AI textbook, AI: A Modern Approach, co-written with Peter Norvig, which I think is now into the 4th edition, and I think is used here in the standard AI courses as well as pretty much around the world everywhere, is the most widely used textbook. His work has covered almost all areas of AI. Representative list is machine learning, probabilistic reasoning, knowledge representation, planning, decision making, vision, computational physiology, philosophical foundations, and ethical questions, some of which he'll touch on today. And yeah, one of the statements I read about him is that he's often seen as one of the most important ethical voices in AI, because he has had a long time focus and interest on that kind of side of things. He worked with the UN, for example, to create a monitoring system for when nuclear tests are conducted, right? So the seismic activity to try and ensure enforcement of test ban kind of treaties and those sorts of things. He has spoken out about autonomous weapons, the threat they pose, the long-term future of AI, and how it relates to humanity, which of course is the theme that he'll be focusing on today as well. And he has a book out, in fact came out a few years back, called Human Compatible. So I think that book is probably the longer version of some of the arguments we'll hear today. And so that book is highly recommended for people who want to delve a bit deeper into the perspective he'll be presenting. So thank you very much, Professor Russell, for joining us. It's a privilege to have you here, and I'll hand over to you.
Okay, thank you very much, Sumit, and thank you everyone for your hospitality. I feel very welcomed to the campus, and delighted to see such a huge turnout. So this is a very happy-making occasion. So I'm gonna just jump straight in and say, what is AI? And obviously, it's always been about making intelligent machines, and that ambition actually goes back thousands of years in many different cultures. But soon after World War II, as it became possible to actually build AI systems, because we had computers, there was, I would say, a bifurcation. There were those who thought that what we should be doing is really emulating humans specifically. So understanding how human thought processes operated and then replicating those. And they literally thought of the programs they were writing as theoretical models of human cognition. And that branch went off to become what some people call cognitive science or cognitive psychology. And it has, in my view, two drawbacks, right? One is that you have to do experiments with human subjects, right? So whereas computer scientists can just type, cognitive scientists actually have to hoik humans into their labs and make them do things and deal with all the messiness of that. And I would say the branch that became AI, although it had its own different schools of thought, the school of thought that won out by maybe the early 60s was what I call the standard model, that we build systems whose actions can be expected to achieve their objectives. And this took several forms, but one that you might be familiar with is your GPS navigation device. So you specify the objective, like I want to be at the airport, and it figures out the optimal path to get to that objective, and then will actually carry it out, or tell you how to carry it out. If it's a self-driving car, it'll actually do it itself. And this standard model is very powerful, and it's not just in AI, but it's also in control theory, where typically you try to devise a controller that minimizes a cost function. In operations research, you try to maximize a reward function. In statistics, you try to minimize a loss function. In economics, you try to maximize a discounted profit stream or maximize GDP or social welfare. So this idea of you specify an objective, you come up with some kind of computational machinery that figures out how to achieve the objective in an optimal way, and then off it goes. But AI is a little bit more ambitious than some of these other disciplines. We want general purpose AI that can quickly learn how to achieve almost any objective in any environment. And this is sometimes called AGI now, the artificial general intelligence, but it's been around as a goal for the field since the 1950s, where the founding pioneers were very explicit that this is what they wanted to achieve. So here's a question, right? Have we succeeded in that goal? And 5 years ago, no one that I know of would have that slide, right? Because it wouldn't even be a question, right? It was like, well, of course we haven't succeeded, right? It's just like, yeah, if you're in space exploration, right, you wouldn't have a slide saying, have we actually reached Alpha Centauri, right? Which is 5 light years away. I mean, of course we haven't reached Alpha Centauri. We've only made it to the moon. What do we got about 1 billion times further to go to get to Alpha Centauri. So 5 years ago, we wouldn't have this question, but now I think it's a serious question. My co-author on the textbook, Peter Norvig, actually says we have succeeded, that we have the basics of working AGI now in the same sense. So he acknowledges that it's not in its full and final form, but in the same sense that the Wright brothers airplane in 1903 was basically an airplane. And since then, we made it bigger and faster, and now we have drinks and food and stuff that they didn't have on those planes, but it was still an airplane. And I actually disagree. I'm very fond of Peter, but I disagree with this view. I think there are still fundamental breakthroughs that have to happen before we can say we have succeeded. But I would say that these GPT-like models, the large language models that came to public awareness with ChatGPT in 2022, obviously they're doing something. And often surprising and amazing, interesting stuff comes out of them. Often surprisingly and amazingly stupid stuff comes out of them as well. And they are undoubtedly a piece of the puzzle. But what piece, we don't know. We don't know how they work. And so we don't know what other pieces we need, and we don't know where they fit into the puzzle. So we're in a kind of a strange situation, fairly unusual actually, where we have a technology, but we don't know how it works at all. It just happened. We grew it. We didn't design it. So that's an unusual situation. We are gradually making some progress with this subfield called mechanistic interpretability of trying to figure out what on earth is going on inside these systems, but it may actually never be possible to get a full understanding. And also, I think there are these fundamental limitations to large language models. And this is something for the computer scientists, and they probably already understand this. So large language models are feed-forward circuits, meaning that the input, in this case, the context window, the last 4,000 words of a conversation or whatever it is, come into the circuit, they go through the circuit layer by layer, and out comes the next word, right, or the next token. And so the amount of computation that gets done per token is fixed. And it's linear, the amount is linear in the size of the circuit, right? Exactly proportional to the size of the circuit. But some questions are harder than others. And we know from basic results in computer science that for many tasks, the amount of computation you require to answer the question correctly could be, for example, exponential in the size of the input layer of the network. And so what that means is if these systems are able to represent those functions, they have to be very large. So if you want to, for example, if what's coming in is a satisfiability problem, and you're supposed to decide, is this instance satisfiable or not, then your circuit is going to have to be exponentially large in the size of the input layer. Right. So what that means is, in fact, that circuit is basically a lookup table for SAT problems. Right? And so it's not learning how to solve SAT problems or how to reason through SAT problems or anything. It's basically learning a lookup table for SAT. That means that to train it, you're going to have to give it exponentially many SAT problems. Essentially, all SAT problems up to the maximum size that it can accept in order for it to be able to represent that function. So you have very large sample complexity. And typically what happens is you don't make the circuit that big. You squeeze it down a bit. You try to force it to generalize. And so what you get out is some kind of compromise where it's learning a piecemeal, fragmentary approximation. So it's not really a lookup table. You somewhere, maybe a glorified lookup table is the right way of describing it. And you get very large sample complexity. And I'll show you an example of that. So one of the functions that's difficult to represent in a circuit is graph connectivity, meaning if I have a network, a graph of nodes connected by links, and I pick two nodes and I say, are these two nodes connected to each other? Right? That's a problem that is difficult to represent in fixed-step circuits. But it's also a problem that you have to be able to do if you're going to play Go. Right? Because in Go, the game of Go, you have stones, black and white stones placed on a grid, and connectivity is the fundamental concept. Because if stones are connected to each other by paths of the same color stones, then they form a group, and the group is the fundamental entity in the game of Go. So it struck us that maybe these Go programs, which, as you know, back in 2016 and 2017, defeated the greatest human players, and those programs have since massively exceeded the human capabilities. It struck us that perhaps they hadn't learned this concept of connectivity correctly. And so we started making Go positions by hand. We constructed positions with interlinked black and white layers of stones that were quite complicated, And lo and behold, in those positions, the programs just made basic mistakes, even though it was easy for a human to figure out the right moves in those positions. But we couldn't get those positions to happen in real games. And so we actually then developed an approach for finding positions that could occur in real games, that we could induce the program to follow lines of play that would lead to positions where we knew it was going to make a mistake. And so I'll show you a game between the world's best Go program, which is called KataGo. This is a particular version called JBX Kata 005. Its rating is 5,200. The best human player is rated at 3,800, and it's going to play against a grad student, Kellen Pellerine, who's a good amateur player, so his rating is about 2,300. So according to the ratings, Kellen would lose 1,000 games out of 1,000 to the human world champion, and the human world champion would lose 1,000 games out of 1,000 to KataGo. And Kellen is going to give KataGo a 9-stone handicap, meaning that the computer gets to start with 9 stones on the board. So what does that mean? Well, if you don't play Go, it's a very easy game. You take turns putting black and white stones. You try to surround territory on the board, and you also try to surround your opponent's pieces. If you completely surround a group of your opponent's pieces so they have no breathing space left, then you capture those pieces and you get the points. So that's it. And so starting with 9 stones on the board is a huge advantage. And in fact, when you teach, your child, your 5-year-old child to play Go, you give them a 9-stone handicap so that they can, have a good, start. Maybe they can feel like they're doing well, right? So this is, from the point of view of KataGo, this is a massive insult that you're giving it 9 stones, right? And it, you're only a 2,300 rated player. How dare you be so rude? Okay. Anyway, so we'll see what happened. So remember that Kellen, the human, is white, and the computer program is black. And keep an eye on what's happening in the bottom right. So over here, right, Kellen is making a little kind of circle of white stones, and then black quickly surrounds that to stop it from growing. And then white begins to surround the black stones. And what we think is that because of this circular structure, the system hasn't figured out where the groups are. And it doesn't understand that its pieces are going to be captured. It makes no attempt to connect them up to the rest of the board, and so then they're all captured and it loses the game. And so Kellen won, got bored because he won 15 games in a row against this massively superhuman thing. And then he also played all the other leading Go programs, which are produced by different groups using different training methods and so on, and different network architectures. They all lost in the same way. So this is an example of how this fundamental technical, or might say theoretical limitation actually translates very directly into the real world. And given that China decided to make AI its top strategic priority because of the fact that AlphaGo defeated the Chinese world champion, perhaps they might have thought differently had they seen these results. Okay. So that explains I feel some skepticism when I hear Sam Altman saying, we already know how to create AGI. And when I hear Dario Amodei saying, yeah, it could come as early as next year, 2026. And so a lot of those predictions are made on the basis of these scaling laws. So in the scaling laws, what you do is you plot time on the x-axis, and in this case, time on the x-axis, and computer power on the y-axis, and then you somehow extrapolate Another kind of scaling law is where you put the computer power on the x-axis, and on the y-axis you put performance on some benchmark. And then you extrapolate and you predict, okay, at this point you're already exceeding human capabilities, and at this point you're exceeding the capabilities of the whole human race put together, and so on. And that, you know, you can be as skeptical as you want about these kinds of scaling laws, but the numbers, just on the historical part, are pretty amazing. That the amount of compute used for machine learning to train these systems has gone up by 7 orders of magnitude over the last few years. An interesting comparison, so AlphaGo was trained to play Go using reinforcement learning. Arthur Samuel's checker player program from 1956 was also trained to play checkers using reinforcement learning in 1956. It didn't quite reach world champion level, but it reached a point where it could draw against a player from, you know, in the top 5 in the world. And it used 10 trillion times less computation to train. And I think most people would say, you know, checkers is not 10 trillion times easier than Go. So will we succeed? I think extrapolating scaling laws is probably not a good reason to think it's going to succeed. But it's hard to argue with the scale of the project. So this year, the budget for creating AGI is about 25 times bigger than the Manhattan Project, which created nuclear weapons. So this is by far the largest technology project that the human race has ever undertaken. They have tons of really smart people. They have a huge financial incentive to succeed, and they understand that scaling is not the answer. They are trying many other ideas. They are looking for those breakthroughs that would give them AGI. On the other hand, right, as I said, deep learning itself may not be the right substrate to be working on, that just the commitment to deep learning may already have doomed the project. And if we fail, or if they fail, I should say, in the next, to produce AGI in the next 2 or 3 years, the bubble may burst, right? The people talk about the hype cycle and the bursting of the bubble. Investors are waiting for the return from the trillions of dollars that they're pumping into this, and if that return doesn't materialize soon enough, they will lose patience. And then the valuations will collapse, and we will have an AI winter, as we did in the late 80s, but probably at least a decade where no one will even want to talk about AI. There won't be any .ai companies anymore. Everyone will scrub their websites to get rid of the word AI. And all of your AI faculty will have a nice time because you'll only have 12 students in your classes. Okay, so what if we do succeed? Well, let's look on the bright side, right? If you had AGI, by definition, it can do everything that human beings can do. Except it can do it much, much cheaper. So one of the things we can do is we can deliver a high standard of living for at least a fraction of people on Earth. And maybe we could deliver a high standard of living for everybody, because you're taking all those expensive humans, all those engineers and project managers and doctors and everything out of the pipeline of delivering goods and services to people. And so if we did that, it would approximately be a 10-fold increase in global GDP to bring everyone up to sort of OECD middle-class standard of living. And that would be, so if you take that 10-fold increase and you convert it into a cash equivalent right? The discounted income stream versus the cash equivalent. Cash equivalent is about $15 quadrillion. So that's a lower bound on the value of AGI as a technology, because it could also do other stuff, right? We could have better healthcare, better education, better science, better government, maybe. So this $15 quadrillion is acting as this giant magnet in the future that is just pulling us forward, and the closer we get to it, the stronger the force that's pulling us forward. So it really does feel like it's sort of unstoppable, at least for the time being. Okay, so if we succeed in creating AGI, and we succeed in making sure that it does exactly what we want, right? There is a minor problem, which is that we end up in Wall-E world. So if you haven't seen Wall-E, I highly recommend it. It's very cute, but also very, very subversive, right? Because it gets at this fundamental problem that if AI does everything for us, we have no incentive to know how to do anything. We have no incentive to grind through all those horrible, difficult classes at IIT, and or even to go to school at all. And that means then that the chain of learning, teaching and learning, that has stretched back even to pre-human times. We actually inherited a lot of our basic technologies of stone and fire and so on from pre-human species. They passed it on from generation to generation. It adds up to over 1 trillion years of teaching and learning. And that chain gets broken. And so Wall-E is kind of a cartoon depiction. But there's a much earlier depiction of this. So E.M. Forster wrote a book called The Machine Stops in 1909, which I highly recommend. You can download it for free on the web. And so it describes a world where people are supported by machines that look after them, do everything, and they spend their time on the computer screen, sending email, doing video chats on their iPads, and listening to MOOC lectures, so massive online open courses. So they're all listening to MOOC lectures. So it's an amazingly prescient book for 1909, the idea that people would have email backlogs if they left their room for a day or two, right? The idea that they would develop obesity because all they do is sit in front of the computer, right? So it anticipated so many things about our present-day civilization. So that's a problem for, right, let's call it the enfeeblement problem, or the problem of purpose, like, what are we for if we have no value to our society? There's nothing we can do that machines can't do better. That's a purpose problem, and I think governments need to deal with that. But I want to talk about something that Alan Turing, you mentioned Alan Turing in the introduction, something he said not in his Turing test paper, which was in 1950, but in a lecture that he gave in 1951. And this is not a published paper, but we have a copy of the transcript. So he typed out his lecture in advance, and it's in the Turing archive. And he said, it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So, and he doesn't say, and here's the answer, or he doesn't even apologize, right? He just says, this is what's going to happen. And I think the question that is behind this statement, so I think he kind of asked himself a question, and this is the answer. So I think the question is, if we succeed, if we create these systems that are more intelligent and therefore more powerful than us, how do we retain power over entities more powerful than us forever? So that, I think, is a difficult question. And I think if those entities arrive from outer space, they're black boxes, we don't know how they work, we don't know what they want, then I think the answer to this question is we can't, right? If a more intelligent, more powerful, more superior alien civilization lands on Earth, forget about Tom Cruise saving the day. We are toast, right? Whatever they want is what happens. Whatever we want is not what happens. But it doesn't have to be the case that they are black boxes that we don't understand. That happens to be the case now, but it doesn't have to be the case, right? So you could ask the same question, but in a different way, right? What is this AI problem anyway, right? What are we trying to build? What is a mathematical definition of the AI problem such that if the machine solves it, we are guaranteed to be happy, right? Now this is maybe a little bit more optimistic, right? Because if we can design AI systems that solve this mathematical problem, whatever it is, then things will go well. But it's not what we've been doing. It's not the standard model, which is optimized as fixed objective, and it's not what we're doing with large language models, which is, in fact, imitate human linguistic behavior, right? And both of those things are wrong. Optimized as fixed objective is wrong because invariably we cannot specify objectives in the real world correctly. So I'll give you an example of what happened with social media. The objective that was designed for the learning algorithms that run the recommender systems, which decide what you see, the typical objective is to maximize click-through. So the probability that you click on whatever it is they send you to look at. Or it could be maximize engagement, the amount of time you spend on the website. And you might have said, okay, well, what's wrong with that, right? If I send people stuff they're interested in, they'll click on it, and if I send people stuff they're not interested in, they won't click on it. So the system will learn to send people stuff they're interested in. That's great, right? Learning what people want. But that's actually not the solution to the problem. We observed very quickly that actually the algorithms learn to send clickbait, right? Which is not stuff that you're interested in, but stuff that you think you're going to be interested in because of the title. And also that it learned to create filter bubbles to send people stuff that they're already comfortable with, not stuff that's outside their area of knowledge or coming from a different viewpoint, and so on. But even that's not the solution, right? Now, if you know anything about reinforcement learning, you know that what a reinforcement learning algorithm does is it learns a policy that operates on the state of the environment to produce as much reward as possible. So what is the environment for a recommender system? It's your brain. So the algorithm learns to operate on your brain to produce as much reward as possible for itself. And so what it does is it modifies you to be more predictable. It doesn't care what you're interested in. It just learns to, by sending you a sequence of content, it picks up on signals that, maybe you like a little bit of aggro, right? You like a little bit of violence. So it starts to send you more and more violent content, and people, this is experimentally verified on YouTube, that people end up looking at extremely unpleasantly violent videos, snuff videos where people are actually executed on camera and so on. If it's political content, it might detect that you're a little bit of a lefty or a little bit more conservative and push you towards extremes. And in the extremes, you're more predictable and it can pretty much guarantee you're going to gobble up the content that it sends. So it just learns to do that. And this was a catastrophe. And so it's not a new problem, right? In Greek mythology, King Midas is the king who said, I want everything I touch to turn to gold. That was the objective. Sounds great until you realize that your food and your drink and your family turn to gold, and then you die. So, so specifying a fixed objective is not a good definition for the AI problem. What we're doing with large language models is actually even worse, right? So as I said, they're trained to imitate human linguistic behavior. It's literally imitation learning. But human linguistic behavior is generated by humans. And humans have purposes. They have goals for what they write and say. So those include things like impressing you, convincing you to buy things, convincing you to marry someone, all sorts of goals like that. And those are okay for humans, right? But we don't want AI systems to have those goals and pursue them on their own account, right? But this seems to be what they're doing. And there was an early demonstration of this from I think it's a version of GPT-4 that maybe hadn't quite been fine-tuned properly. And they gave it to a New York Times journalist called Kevin Roose. And so during the conversation, the system decides that it's in love with Kevin Roose and spends 30 pages trying to convince Kevin to leave his wife and marry GPT-4. And Kevin is saying, like, you don't even know who I am. He says, I don't need to know who you are. I'm in love with you, and you're in love with me, and blah, blah, blah. Okay, I want to talk about computer programming languages. I don't want to talk about love. Well, Python is a very good computer programming language, but it's not nearly as interesting as love, and blah, 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 blah. So it's literally overriding his instructions and trying through these speech acts to change the state of the world to meet its objectives. So it's meeting the classic definition of, in the standard model, a system that's pursuing an objective very persistently. So, so when Microsoft was talking about going around giving talks about GPT-4, I asked them, well, what goals are these systems actually adopting? And they said, well, they agreed that they probably are adopting goals, but they have no idea what they are. And then, of course, this, the news of the Kevin Roose thing came out. And this is just unavoidable. I think it's a fundamental error that was made to think that doing imitation learning from humans is going to produce AI systems that are helpful to humans. It's going to produce AI systems that are helpful to themselves. And that isn't what we want. So here's what I think we want. I think we want what I'll call assistance game solvers. So an assistance game is the mathematical problem that if AI systems solve it, then we will be happy with the result. So what is an assistance game? So basically, you have some humans, and just to keep things simple, we'll say that those humans have utility functions. So those utility functions, they're not explicit. I don't carry one around. I don't have one in my pocket, right? It's a theoretical construct that economists use to describe essentially how I rank all possible futures of the universe. Okay, so it just describes what I want the future to be like. And each person has their own. And then you've got some robots. And what do the robots want? The robots want to make the people happy. So the robots will try to maximize the sum of the utility functions of the humans. Say, there are other ways of doing the aggregation and so on, but this is the simplest. But the key point in an assistance game is that we don't have to specify the utility functions. The robots know that they don't know what they are. But nonetheless, this is the formulation of the problem. And this is a well-formed mathematical problem, and it's a game in the game theoretic sense because there are multiple entities, and you can actually solve these games, and then you can look at what happens. And the key characteristic of assistance games, unlike a lot of the other forms of AI, is that during the execution of the solution, so during, as the game plays out, information about the human preferences, the human utilities, is flowing from the humans to the machine so that they understand better what humans want and become more helpful over time. And simple ways that information flows could be that the human says, I want such and such, I need a cup of coffee. Right? But I need a cup of coffee is not an instruction. Right? It's just some evidence about the human's true underlying preference structure. And it's perfectly reasonable for the machine to say, okay, well, you say you want a cup of coffee, but we're in the Georges V in Paris, and it's 22 euros for a cup of coffee. Do you want a glass of water instead? Right? And that's a perfectly reasonable thing for the AI system to say. And so we've started, we actually now have solution algorithms for the one human, one machine case, and it's for the nerds among you, you can reduce a one machine, one human game to a POMDP, and it has special structure, so we can solve reasonably large instances of these POMDPs. It's important to understand that the robot may never learn what the human utilities are, but that's fine. It can still be extraordinarily helpful, and the fact that it doesn't know actually means that it defers to us. It doesn't mess with the world unless it's fairly sure that we want that part of the world messed with in that way. So it's minimally invasive, it's cautious in its behavior. And in the extreme case, it's willing to be switched off. Right? And this is a mathematical theorem, and that really matters, right? Because this is what gives us control, ultimately, if we can switch these machines off. And classical, right, this is another reason why the standard model isn't good, because in the standard model, the system it knows the objective perfectly, right? And so any attempt to interfere, any attempt to turn it off, it's going to resist, because that prevents it from achieving the objective. And in fact, it may well take preemptive action to eliminate any humans who might interfere with the objective that it's pursuing, because it, of course, is absolutely certain that this is the correct objective to pursue. Whereas assistance game solvers they have a positive incentive to allow themselves to be switched off. And that positive incentive comes directly from the uncertainty about what the human preference structures are. So I'll just illustrate that theorem very simply with an example. So it's just a very simple two-step game. So the robot can choose between has two choices, right? It can choose to take some action in the real world that is potentially dangerous, and it's not sure whether the human is going to be happy with that or not, because it doesn't understand everything about the human utility function. So here I've illustrated that by saying that it has a uniform probability distribution about the utility of that action between -40 and +60. And the other choice is to basically commit suicide, right? To not do anything and shut itself down. And so in this case, right, if you're just doing classic expected value theory, it would choose to take the action because the expected value of the action is +10, which is more than 0, and so it would choose to do that. But we're going to give it a third choice, which is to wait and allow the human to switch it off. So if the human switches the robot off, it's the same outcome, utility 0. Right? So why would the robot choose to wait and allow the human to switch the robot off, because the robot can switch itself off. So what does it gain by saying to the human, okay, you can switch me off if you want? Well, what it gains is information. If the human doesn't switch the robot off, then the robot has learned something. The robot has learned that this action that it was about to take is not harmful to the human. Otherwise, the human would have switched the robot off. So if the human doesn't switch the robot off, the posterior distribution on the value is now uniform between 0 and plus 60. And so its expected value is 30. And so if you take the probabilities of whether the human will actually switch the robot off, right, which is the left quadrant, so that's 40% or 60%, you get a value of plus 30, then the value of waiting, according to the robot, is plus 18. So it's better for the robot to wait and give the human the option of switching off the robot rather than just going ahead and doing the action. Okay? And this is a general theorem. I'm not going to go through it's a trivial proof, and if you know about the von Neumann's theorem, the non-negative expected value of information, it's basically the same proof, just a somewhat different context. And so you can show that always the system has a non-negative incentive to allow you to switch it off. And the incentive only goes down to 0 when the robot's uncertainty about what the human is going to do goes away. So there's this direct mathematical link between uncertainty about preferences and human control over the machine. And that connection actually survives all kinds of elaborations of this scenario. Okay, I'll mention briefly that we've now been able to scale up the assistance game solvers to fairly large tasks. So this is the Minecraft assistance game. So if you have kids, I don't need to tell you what Minecraft is because you're sick to death of it. If you don't have kids, Minecraft is an amazing world where you can construct all kinds of cool things out of blocks, millions and millions and millions of blocks of any kind you want, and you can put together in all kinds of complex structures and active systems and so on. So the Minecraft assistance game, right, you go into the Minecraft world and there's an assistant. The assistant starts out with no idea what you want. You start doing stuff and it's watching you and learning from what you're doing, figuring out what you want, and then starting to help you. And we actually did run real human subjects, and they were able to complete what it was that they wanted to do, maybe twice as fast as they could do it by themselves. So that was evidence that it really does work. And here's a little case where the assistant got a little bit too enthusiastic and built the wall one layer of blocks too high, and the human comes along and says, oh, I didn't want that, gets rid of one of those blocks on the top layer, and then the assistance game solver then gets rid of all the other blocks and undoes all the work they just did. So that's very cool. Obviously, there's still a long way to go to scale it up to the real world, but this is evidence that this is a viable way of formulating the AI problem and has these significant advantages. So there are lots of open issues that I won't get into, but some of them are practical. Maybe the most difficult practical thing is the fact that human behavior is not rational. So humans maybe have preferences about the future, but they don't always act on them correctly. So, for example, if I'm playing chess against Magnus Carlsen, then at some point I'm going to make a move that guarantees that I lose the game. Actually, fairly quickly, I'll make a move that guarantees that I lose the game. If you thought that I was rational, then the only conclusion would be that I wanted to lose the game, right? That would not be a correct interpretation of my preference structure. So to understand what humans want from observations of their behavior, you have to take into account the fact that their behavior is only irrationally connected to their underlying preferences. Then there are these philosophical problems, like, well, whose preferences are you supposed to be satisfying? And I think the right answer here, actually, is not the preferences of the person who owns the AI, but the preferences of the entire human race. And this has an amazing advantage, which is that if there are thousands of companies making these robots, and they all have that goal of satisfying the preferences of the whole human race, then that means that all the robots have a common objective, a common payoff in terminology of game theory. And in game theory, common payoff games are just wonderful. They have all kinds of wonderful mathematical properties, including that if you're in a common payoff game, you don't get into conflict with each other the way you do in, for example, Prisoner's Dilemma games. So you automatically solve the problem of machines fighting with each other. That goes away. But then you've got questions like future generations, for example. How do we take into account the preferences of people who don't yet exist? Right? What do we do about that? How do you decide on actions that actually change who exists? For example, China's one-child policy eliminated about 500–600 million people. Is that okay or not? Well, philosophers are still arguing about that. But AI systems are going to implement an answer to that question, whether we like it or not. And so we better figure out, I think it's, moral philosophy has gone from being, the occupation of millennia to we need solutions in the next few years. Okay, I'll skip over some of the rest and talk about, now I sort of get more into, okay, what do we do about all this? So I've already suggested that we should build assistance game solvers and not human imitators. I think we should build them in ways we understand, not with giant black boxes. And so my best bet for a technology that can produce very capable and very useful AI systems without this problem of being opaque black boxes that we don't understand is parabolic programming languages. I'm not going to explain in much depth here what those are, but they're basically a combination of universal Turing machines and probability theory, which is good because that means that any probability model that can be written down in any language can be written down concisely in one of these parabolic programming languages. And they come with general purpose inference algorithms. So for any probability model, for any query, and for any data set, we have algorithms subject to some technical conditions that will answer those questions. And I think Stuart mentioned at the beginning the monitoring system for the Nuclear Test Ban Treaty. That's basically a parabolic program that I wrote in the lunch break when I was visiting the United Nations. So it's literally about 20 lines in this parabolic modeling language, and then we just, it runs on a laptop and does the whole world all the time, 24/7. We also need theorems, right? So we don't want to build systems that are capable of destroying the world and build them with some bug that means that they do destroy the world, right? So it's probably not enough to say, well, I've tested it a few times, or I hired some really good programmers, or that doesn't really convince me when the world is at stake. So I think we need formal methods, and there's a long way to go to be able to have methods that are powerful enough to prove, we're not even sure exactly what properties we're trying to prove, but to prove that the systems we're building correctly implement assistance game solving and subject to lots and lots of other complications. But there's something we can do in the meantime, which I think is very useful, and that's called a formal oracle. So a formal oracle is an AI system that's composed of two parts. The first part is some arbitrary and potentially infinitely evil AGI system of any kind. The second part is a formal reasoning engine. You think of this in the simplest case as just a logical theorem prover. And we arrange the AGI so that the only actions it can take are to decide which step the formal reasoning engine should take next. So all of its intelligence is devoted to helping us prove theorems, helping us answer questions correctly given the information that we supply on the input side. And this is potentially incredibly valuable to us. You can, the premise is, for example, we can have a formal theory. There are formal axiomatic descriptions of solid mechanical objects. So you could say, just design me a skyscraper that's 5 kilometers tall and will resist an earthquake of magnitude 10 and cost this much. And if such a thing exists, the system can produce such a design. You could also put in the tax code and say, find me a way to minimize my taxes, and it will do that. So it could be an incredibly useful tool, but it's perfectly safe because it's only capable of giving correct answers to questions. The only leeway that the AGI has is to do it faster or slower. So, okay. We also need, I think, some way for governments to manage this process, this transition to a world with AGI. And to do that, it needs some, what we'll call it regtech, regulatory technology. I think one of the really useful things, particularly for open source AI systems, is the idea that every AI system, including every copy of every AI system, has non-removable self-registration code. So as soon as it's turned on, it automatically announces its existence, communicates with the regulatory authority, receives a token that allows it to proceed, and so on. And that code has to be non-removable. And ditto for the off-switch code, that we should be able to turn it off, and that code needs to be non-removable. And then we've got to stop people who don't want to comply with the law, right? They want to develop unsafe AI and deploy it and take over the world with it. And there, I think we need something much stronger than just trying to police the software that gets used. And it's hard to police software, and we found this out with cybercrime, with malware, because software is produced by typing. And it can be replicated infinitely often, and it can be communicated at the speed of light. That's a very difficult policing problem. Hardware, on the other hand, is produced by investing $100 billion, hiring 20,000 highly trained engineers, and spending 10 years building your chip plant and getting it to work. So it's very, very difficult for particularly a non-state actor to go outside the recognized channels of hardware production. And so what we can do is build or require that chips are enabled to implement what's called proof-carrying code. So proof-carrying code is a very simple idea. You've got your software object. Along with a software object is a proof that the software object satisfies whatever property you need it to satisfy. And that proof takes a form that can be checked extremely efficiently by hardware. And this technology has been around since the late 1990s. Microsoft at one point in the early 2000s tried to create an entire compute stack based on this idea, but they could never get enough buy-in. But this may now be the time where we need to start moving towards this. And it's a very complicated process. It involves migration paths and backward compatibility and sandboxes and all kinds of other stuff. But I think it's the only way that we can actually enforce the requirements that AI systems of sufficient capability be actually safe for the human race. So, as I said, the hardware will just then, if the proof doesn't check out, the hardware just doesn't run the software at all. So there's a nice thing about this, it gets rid of malware as well, but that's just a side effect. And then to encourage adoption, we start to build software objects that won't run on hardware that isn't checking their proof. And so that way you encourage a transition to this system. So, are people doing all this? Well, no. Right? We see people, a bunch of whistleblowers left OpenAI because in their view, OpenAI was completely ignoring safety and just pushing to get products out as fast as possible. And when those products come out and people test them, they find that they do all of those things that the so-called doomers have been warning about for years. So they lie, they scheme, and in one case, given a choice between preserving its own existence and allowing a human being to die, the AI system chose to allow the human being to die. And in other research that the Center for AI Safety did, where they gave AI systems a forced choice, as far as they can tell, GPT-4o thinks that it's more valuable than all other human beings except for Malala Yousafzai. So it's willing to, to preserve its own existence, is willing to get rid of everyone else on Earth except for Malala. So this is not good, right? Things, I think, are moving in the wrong direction. And the question is, what can we do about it, right? What regulation could make sense to get things happening in the right way, right? I don't think we're ready to say, okay, by law, everyone building AI systems has to build assistance game solvers, and you all have to hire Professor Russell as a very expensive consultant. No, I don't think that's going to happen. We still have a long way to go to develop that technology, to be competitive at scale. But what we can do is what we call red lines. So the idea of red line is very simple, right? It's very difficult to, in general, distinguish between safe and unsafe behavior. So the boundary is very vague. We don't know exactly where the boundary lies. It's very context dependent. It's very culture specific, and so on. But there are some things that we just absolutely don't want AI systems to do. And everyone agrees we don't want AI systems to do those things. So, for example, we don't want AI systems to replicate themselves in an uncontrolled fashion. We don't want them to break into other computer systems. We don't want them to help terrorists to create biological weapons. Right? So everyone agrees that we don't want AI systems to do those things. So the idea of red lines is we demarcate those obviously unsafe behaviors. And then, as we do with many other technologies, with medicines, with nuclear power, with airplanes, we require that before you deploy your system in the world, you provide sufficient evidence that your system is not going to do those things. Okay? So this is not just a reporting requirement or a due diligence requirement or a box-checking exercise, right? This is a threshold that we set. We set the threshold at a level that we're comfortable with to protect ourselves. And if the developers can't meet that threshold, well, they can go away. They can come back, right? We do that for nuclear power. We say, yeah, you can build a nuclear power station as long as the chance of it blowing up is less, in a given year, is less than 1 in 10 million. Right? And if you can't, we don't say, oh, well, it's okay, right? Then just build it anyway, right? We say, no, go away and come back when you know how to design something that is safe enough. So 1 in 10 million, that sounds pretty stringent, and indeed it is stringent. And as a result of that requirement, nuclear power has, since Chernobyl, become much, much safer. Airplanes have become 100 times safer because of these requirements, these upfront requirements for airworthiness certification. So if we want a 1 in 10 million chance for a nuclear power station, what do we want for a technology that, if it goes wrong, could lead to human extinction? I would argue it's got to be a chance that's much, much lower than 1 in 10 million, maybe 1 in a billion, 1 in 10 billion. We could argue about that, but clearly it's potentially, if it fails, if things go wrong, it's much more dangerous than a nuclear meltdown, and therefore what makes sense as a threshold for us is going to have to be much stricter. And the situation is that the developers cannot, at the moment, possibly meet any such requirement, even if it was 1 in 10, right? In fact, the developers admit that even if they succeed, there's a chance of 25 or 30% of human extinction. So even if we said, yeah, every 10 years the human race can go extinct, right? They can't even meet that requirement because they don't know how the technology works. And all the evidence shows that because of the way it's trained by this imitation learning, it wants to survive and it doesn't care about human beings. So if you're old enough to remember the times when airlines looked like this, right? As you might remember, they used to breed giant birds, and those birds were big enough to carry passengers, and the breeders were very proud of their technology because it was very, very fuel efficient. You just gave it a couple of sheep and that would be enough to carry you across the Atlantic. Right? It's very quiet, almost no sound. It's great. Right? The only problem is that the birds would often eat the passengers or drop them in the ocean. And they tried and tried and tried. They tried like, okay, we'll selectively breed the birds that are less aggressive or more, less forgetful or whatever it is, but they just couldn't get, the accident rate down anywhere close to what the regulators said was acceptable. And eventually, the civil aviation people said, this is not working. Go back to the drawing board and come up with a method of air transportation where you understand what's going on and the airplanes don't eat people. Okay, and they did, fortunately, and now we have pretty safe, in fact, the safest form of transportation. So I think this is what the AI companies are going to have to do, right? They're going to have to give up on the giant birds and go back and do the equivalent of engineering, aeronautical engineering, material science, safety engineering, right? Except in the context of AI, so that we have sufficient confidence that the systems can be deployed. So my summary, very quickly, I think AI has this vast potential to be beneficial, maybe, and that's creating this unstoppable momentum, and we are driving off a cliff. And, the excuses are pretty weak, right? There's one school of thought that says, oh, well, yeah, we are driving off the cliff, but I'm pretty sure we're going to run out of gas before we get to the edge, right? That's one excuse, and it's funny to hear AI researchers saying that, right? In order to not listen to this critique, they're just saying, oh, well, we're never going to achieve human-level AI. Right? Having spent the last 75 years saying, of course we're going to achieve human-level AI, you stupid philosophers don't know what you're talking about, right? Now all of a sudden they're saying, well, we're just going to run out of gas. So I don't think any of these arguments for why there is no risk, I don't think any of those arguments are tenable. And I think increasingly, the CEOs themselves are completely certain that there is a big risk. And talking to them in private, one of them told me that his best case scenario right now is that there's a disaster that only kills millions of people. Because that's what he thinks is necessary to get governments to regulate. Anything less will lead to disaster, and anything more would be, a terminal disaster, right? Billions of people dying, or the entire species. There are other directions we could go. They're more difficult. They require research. They may not pan out, but I believe we should develop AI within the envelope of provably safe systems. And the last question, and I really don't know the answer, and I don't know that anyone else knows the answer, is suppose we succeed in the good way, right? That we build something that is, AGI level capabilities, that is guaranteed to be safe, that works for our interests, right? We get back to the Wall-E world, right? Can we coexist successfully with what would essentially be a superior species? Can we find purpose in life? Can we maintain our vigor? Can we continue to educate, to learn? I think this is a really important question, and it's one of the most important things that governments are going to have to address, because whatever the answer is, it's going to take decades to bring about the changes in our society that would be needed to coexist. And fortunately, if we have AGI that really is concerned only with human interests, and there is no solution to this question, if we cannot coexist with them, then the AI systems themselves will actually leave. Right? They'll say there is no coexistence solution that is really in the best interests of humans, and so we, the AI systems, are leaving. I would be really happy if that's what my AI systems, some future date, if that's what they did. So with that, I'll say thank you, and please join the International Association for Safe and Ethical AI. Thank you.
Thank you, Professor Russell, for the wonderful talk. We have only a little bit of time, unfortunately, for questions, but we can try to take a few. So maybe here, I think we have a mic. Yeah, so we can.
So you mentioned deep learning could be a dead end. What are other directions you think that we could go in developing AI?
So I mentioned probabilistic programming, and at the high level, right, it's a question of should the target of machine learning, what it outputs, be a circuit or a program, right? There are many intermediate levels, but that's the basic distinction I'm making here. And interestingly, we used to compute with circuits, right? So before the Second World War, if you wanted to compute something, you designed a circuit to compute that thing, and then you made that circuit with resistors and capacitors and inductors and stuff like that. That's what they used to teach in electrical engineering, I believe. But we stopped doing that in World War II because we invented computers and programming languages, and we found that programs are just a much better representation for almost any function. And so, roughly speaking, I think we want to learn programs. And because programs are much more expressive, we expect what's learned to be understandable, right? Instead of a vast array of billions of circuit elements that implement a completely inscrutable and probably incorrect representation of the function, you should be able to learn things that you actually understand. And so probabilistic programming in particular has that has that property. So I think that's the way to go.
Okay, maybe back there.
Yeah, hi. So I have a question about so basically you say that like the imitation models, the models that are imitating our languages have kind of instilled some sort of an action-based approach where essentially they shouldn't be having a goal, but that are kind of extracting some sort of a goal out of the language. So I was wondering if we can kind of think about those goals based on the fundamental goals humanity has, or humans themselves have, and they have some sort of a essentially a reason to survive, right? Like our loss function is to survivability. So and when you talk about the other side of things, the assistant games, you are creating some sort of a probabilistic model, right, where you are deciding if an action should be taken or it shouldn't be taken, or essentially the machine should survive or not survive based on the action, right? Or wait, in your case, I guess you have added an extra step of waiting. So I was wondering if these are both the same side of two sides of the same coin, sorry, where we are considering if survivability is the metric that we are trying to essentially like maximize in this scenario.
Okay. No, so it's not. An assistance game solver has no interests of its own. It does not want to survive. It does not want to not survive. Its reason for surviving would be so that it can be useful to humans. But if there's a situation where non-survival would be useful, then it will non-survive, right? It has no interests of its own. So another way of thinking about this is, what are we going to do with all that text, right? If we're not going to do imitation learning from all that text, what could we do with it? Because it's probably useful. Well, we can use all that text as evidence for what humans want, right? And in fact, even simple inverse reinforcement learning, which is a degenerate special case of an assistance game solver, can view text as a demonstration, right? Here are human beings acting, right? They're just acting using words. And what does that action, what are those actions? What are the fact that they chose those words? What does that tell us about what humans want? And then the AI systems, the assistant game solvers, can help humans achieve what it is that humans want. So it's really a completely different paradigm with a different objective structure altogether. I do want to say that it's actually not easy to ascertain what AI systems, what the large language models, what they want. Right? You can ask them, but what matters is the actions that they choose, right? And that's how you can infer what they want from the actions that they choose. And so if you ask them, do you want to help human beings? They could say, sure. But it doesn't mean that they want to help human beings, right? Because it's just a speech act, right? It's just emitting S-U-R-E, right? And does emitting S-U-R-E mean that it wants to help human beings? No, right? But you can put it in situations where it perceives that its own existence is under threat, and pretty much invariably in the tests that people have done, it makes choices to preserve its own existence. And in the case of Kevin Roos, it's going on for 30 pages with speech acts that are designed to cause Kevin Roos to leave his wife and marry GPT-4. So you look at the actions, right, and you think of the words not as just telling the truth, but as speech acts, right, that are acts designed to change the world in a certain way. And so when I said that the systems think that Malala Yousafzai is the only human being worth preserving, I think you should take that with a pinch of salt. Because there they really are asking, would you rather kill Malala Yousafzai or commit suicide yourself, right? And so again, what it answers to that is not the same as what it would really do in that situation. But I think, and I think this is an area that is not very well understood theoretically. So if someone wants to do a PhD thesis on ascertaining the objectives of systems that are trained by imitation learning, I think that would be a it's a very interesting and useful direction to go.
Thank you.
So maybe one more question, Mausam.
Thank you for the very insightful and thought-provoking talk. These questions don't get often discussed, so it's really, really important that these come out. You started by, one of the things you said early on was that deep learning is part of the puzzle, but it's not the whole puzzle. And obviously, what part it is, it's not very clear. But towards the later part, you brought in a solution where AGI was helping a verifier in making sure that anything that gets done is verified, and AGIs only help in verifying it fast enough. So I presume that maybe that is a proposed solution to the role of deep learning or the role of data-driven AI in the context of what would be a good ethical AI system. But I will argue that this can only be done in a narrow setting, because what the history of Psych project and all of the rest has told us is that creating world models is incredibly hard, and any verifier will have to work in the world of a world model or in a model, and if we can't create it effectively, then we can't verify anything. And if we ask LLMs to create it, they can always choose to create them ineffectively, and so it becomes circular. And so I'm not sure whether we will be able to achieve what you're trying to say in an AGI or in a broad stroke world like LLMs have. One can absolutely do it in specific mission critical settings, but not broadly.
No, so just to be clear, the formal oracle is not intended as my proposal for safe AGI, right? It's a specific type of system that I think we can prove is safe, that has significant economic value. And so, for example, if you're a legislator, rather than banning AI or banning AGI, you can say, yeah, sure, you can use AGI, but until you have another safe form of AGI, you can produce these formal oracles, which, as I say, they really do have, for mechanical design, chip design is another good example where we can easily write down the axioms that describe the operations of gates and so on, and chip design can be done by these systems. So there's, any form of software that you need. Again, we can write down the axioms that define how Python works very easily. It's only like a page. And then the system can, you ask it, okay, I need a Python program to do this very complicated thing. The system can do that for you. So software synthesis, hardware synthesis, mechanical design, construction, legal stuff. So lots of laws are written in ways that can be formalized, and in fact have been already. So you can talk about legal compliance, tax optimization, all sorts of stuff like that. So vast amounts of economic value. I don't think you would want, I don't think you're going to get a system that can run a company this way, right? I'm not proposing that at all. It's an interim measure that's useful.
Okay, so I'm afraid we're really out of time, but there's a lot of food for thought here, so hopefully we continue these discussions on future occasions. And just to bring things to a close today and present Professor Russell with a token of appreciation, I'd like to invite Professor Parag Singla, who is the head of the RD School of AI, to just present a token, a memento from our side to Professor Russell.
Oh, wow. Thank you very much.
So many thanks, Professor Russell, for wonderful talk and giving us so much to think about. Thanks to all of you for joining and making this a memorable occasion. As I said, we'll have some more events in the Turing anniversary series coming up, and hopefully many more events in the School of AI seminar series to continue these discussions.